So today we're going to use our transformation information to work with our next function called the absolute value function. So first of all, let's just take a look at the warm-ups. So the warm-up asks, describe how G changed from F. So what happened? Well, if I take F and add 7, that means it's going to be moved up 7. So if I was down at -5 and I moved up 7, I'm now at 4x plus 2. So all you had to answer that it was translated up 7. Okay, in this one, what this is saying is just a reminder that you're going to take this and now you're going to translate it right 3. Remember, a number added or subtracted. Added means up, subtracted means down. A number with the x is the opposite. This would move right 3. Okay, so now to start our absolute value function, we are going to use our XY chart and put in several values so that we get an accurate graph of our parent graph. So I chose basic integers of -3 through 3. So I want you to go ahead and stop the video, make an XY chart, and I want you to plug those values in. Remember, what does absolute value do to a number? It makes it positive. Okay, so I could have plugged in anything I wanted. I could have plugged in a half. I could have plugged in -10.75. I could have put in, my domain could have been anything, which remember, anything means all real numbers. So when I put in -3, I got out 3, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, and 3, 3. So when I go to graph those, at first this looks like it's going to be linear, so that part we could see, but because this is an absolute value, it's like it took this line, our parent graph line of y equals x, and swung it up. Okay, so how would I describe the domain and range for the absolute value function? Well, let's look at it. First of all, if I made my XY chart, I chose nice numbers. I chose negatives, positives, and 0, but they were all nice numbers. I could have put in anything I want. So remember, that would mean all reals. And you can write all reals, or this is the symbol, the fancy notation, -infinity to infinity. Now, when I'm looking at the range, I need to look at my y values. Notice I don't get any negatives. So I do get 0 and I do get positives. So my range is all positives bigger than or equal to 0. So I could write this as 0 to infinity, or if you just want to write it, y is greater than or equal to 0, that is fine. Now, a characteristic of absolute value graphs that a linear function did not have is a vertex. And a vertex is either highest or lowest point of the graph, and the vertex of your parent graph is 0, 0. So when you go to translate a absolute value function, you're going to be changing the vertex. So let's take a look at example 1. So example 1, we are making transformations to the equation, and we should know what's going to happen to the graph based on that, and we're going to name the domain and range and the vertex. Okay, so looking at this graph, I know that if I'm subtracting 3, I'm going to be moving this down 3. So I'm going to be taking this graph and translating it down 3. So therefore, my vertex is now 0, -3. Now, if I didn't know transformations, I could make an XY chart for all of these, but I think you're going to see that knowing transformations and knowing the parent graph is going to be very helpful. I don't have to make an XY chart to graph this. I could if I wanted to, if I wasn't sure. I can always put in a couple of values just to make sure. All right, but now look at the range. Okay, this graph moved down on the y-axis. Isn't everything, all my y coordinates, or look at my y-axis, bigger than or equal to -3? So this is the fancy notation, -3 to infinity, or you could just say y is greater than or equal to -3. Since the graph moved down, it included more y values. So my vertex is 0, -3. Okay, let's take a look at example 2. So again, we could make an XY chart and graph this, but I encourage you to know your transformations. So this +2, remember, means that's going the opposite direction. It's going to move it left 2. This is inside the function, not on the outside. Okay, so if it's moved left 2, that means my new vertex is at -2, 0. Again, you could make an XY chart to get that graph, but it helps to know transformations. So if I were making an XY chart, you know, I hope you're starting to see the pattern that I can put anything I want into absolute value. My domain is always going to be all real numbers. Okay, now my range. A lot of people want to put on this one -2 to infinity. Remember, range is your y coordinates. Did I move up or down on the graph? No. Look at my y coordinates. Isn't my y going to be bigger than? Isn't it all positives, including 0? So it's everything greater than or equal to 0. If I did not move up or down, my range did not change. Okay, let's take a look at example 3. So I have a translation. I'm subtracting 4, which means take the opposite. So I'm going to be moving right 4. So now my vertex is 4, 0. Any absolute value function, I can put in anything I want. So if I were making an XY chart, you could put in anything. It's always all reals. But now my range, I have to look at my y coordinates. I have to look at my y axis. Did my graph move up or down from the parent graph? It did not. So that's why my range is everything greater than or equal to 0. Okay, let's take a look at example 4. All right, we are adding 5 away from the function. So we know then that means it's going to be moved up 5. Okay, so if I'm moving up 5, again, absolute value, if I wanted to graph this and use an XY chart, I could put in anything I want. So hopefully you've caught on, domain is always all reals. Now my range, okay, my vertex is now 0, 5. Is there any point on my y-axis or my range below 5? No, that's why my range is y is greater than or equal to 5. Okay, so the next problems are asking us, you don't necessarily have to name the domain and range, but you name the transformation and graph it and name the vertex. Okay, so first of all, this is inside with the x. This is going to move right 1 and up 2. So if I were you, I would right away, if that means move right 1 up 2, that means my vertex is 1, 2. And I would graph that. All right, now, if I wanted to show you this is something I didn't want to bring up too soon, but don't all absolute value equations have a line of symmetry? So if my vertex is at 1, 2, I may want to plug in 3 to get another point. So 3 minus 1 is 2. Absolute value of 2 is 2. 2 plus 2 is 4. So 3, 4 would be a point in my graph. I may want to plug in 2, and I would get 3. Okay, and then I could graph their reflection points. All right, let's take a look at example 6. All right, down 6. This is going to be moved down 6. The negative on the outside means it's going to be reflected or flipped upside down. So the vertex is 0, -6. Okay, now I didn't ask this, but my domain, of course, for any absolute value, I could put in anything I wanted. It's all reals. Now my range, look at the y-axis. Are my y's ever bigger than 6? No. All right, next one. Ooh, we got a lot going on here. Again, I always find my vertex first. I would move right. This moves right 4. Remember, inside the function moves left or right. It's the opposite, -4, so it moves right 4. I go up 3, so that means my vertex is 4, 3. All right. Now, what does this 2? When I multiply my x by a 2, doesn't that mean it's a vertical stretch? It's twice as tall. So how do you show that in a graph? Well, this is what I started to talk about in one of the graphs. If you know your vertex is 4, 3, I would put in an x around that. So if I put in 3, 3 minus 4 is -1. Absolute value of -1 is 1. 2 times 1 is 2 plus 3 is 5. So I would get 3, 5. And because this has a line of symmetry, 5, 5 would be a point. Now, I want you to also notice a difference. The 3 and the 5 are right next to the 4, right? And weren't these y-coordinates 2 away from the vertex instead of 1? That's because it's vertically stretched. Okay, I'm going to skip example 8, and I want to go to example 9. So now we are going the opposite direction. I'm giving you the graph, and you're going to write the equation. So the first thing I would do is I would find my vertex. Well, I wrote that it's reflected, so I know a negative is going to be involved. But my vertex is -2, 4. So a vertex of -2, 4, didn't that mean I moved left 2 and then up 4? So if I were starting this out, what I would have done is All right, I know my left 2 has to be inside with my x of the absolute value, so that's an x plus 2. Up 4 means I added 4 on the outside of the absolute value, or the x. And what does a reflected mean? That I put a negative on the outside. Reflected, think of that meaning opposite. Okay, last one. Again, when you're going backwards and I'm asking you to write the equation, I would encourage you to find the vertex. So my vertex is 4, 2. So that means I went right 4 and up 2. So the first thing I would do is, if I went right 4, that means absolute value of x minus 4, and then I went plus 2. But now, here's a little bit of a challenging part. Take a look at the vertex 4, 2. Look at 3. So if I make my xy chart here, my vertex is 4, 2. But if I look at my 3, isn't that up at 4? And if I look at my 5, isn't that up at 4? So do you see these are 2 away? So that's why that is a vertical stretch of 2. Okay, so lots of information. What should you get out of this? You should understand the basic absolute value graph. You should know what it looks like. You should understand domain and range, and you should be able to identify the vertex. Now, instead of making a bunch of XY charts to graph the absolute value function, we're using the idea of transformations to make that easier.